Now that we know when we can use the normal approximation for a binomial distribution, let's talk about the actual how we do that. So ultimately what we have to do is think about the difference between the binomial distribution and the normal distribution. So remember, the binomial distribution is discrete, and so it's going to be represented by a histogram. And yet normal distribution is a symmetric distribution. Okay, so now that we know when we can use the normal distribution to approximate a binomial distribution, let's talk about the how. So we know that the binomial distribution is discrete, and so it can be represented by a probability histogram. And so then to calculate exact binomial probabilities, our formula for the binomial formula would be used for each value of r, and then we add those results up. And so typically that corresponds to areas of bars in the probability histogram. Now the issue with that is our normal distribution is a continuous distribution. So what we have to do is essentially, when we're finding it for the area, we've got to get the entire rectangle's width. So when we know the value x is equal to some value c, remember the issue with that is we can't find area under a normal distribution at one point, right? So what we have to do is we have to make this become so we have to correct this to become continuous. So basically what we do is we figure out, okay, what are the edges of this rectangle? So remember, to do that, we essentially do our class boundaries. So if we know x is equal to c, then to get this value, we do c minus 0.5 and c plus 0.5. So that's the idea for correcting this to become a normal distribution, or approximately a normal distribution, is we basically extend, instead of having just that one value of something, we take it out to the edges of the histogram, the bar on the histogram. So we're taking this back out. So all we're doing is we're really finding the class boundaries the same way that we did back in chapter 2. So let's use a correction for continuity to convert binomial intervals to a normal distribution interval. So the probability of getting between 270 and 310 successes inclusive. So let's first write out what this binomial variable is. And I'm going to use r for binomial and x for normal, just so we can keep track of which distribution we're in. And remember, if I'm changing variables, I have to do some kind of calculation. In this case, our calculation is going to be our continuity correction. So either adding and or subtracting 0.5, depending on the type of interval we have. So if we want the probability of getting between 270 and 310 successes inclusive, then this is the probability that r, because we're in binomial, inclusive means we're including, so we have equality. So r is between 270 and 310. So this turns into the probability that 270 is less than or equal to r, less than or equal to 310. And so now we want to do the continuity correction for this. So if we think about this interval on the number line, if we were finding our rectangles, so we know we're between 270 and 310, but then those bars for our histogram actually stop at 0.5 below and 0.5 above those values. So if it's a left endpoint, what you want to do is subtract the 0.5 from it. So in this case, if we're converting to x, this is going to be 270 minus 0.5, less than or equal to x, because I'm doing my calculation, I'm doing my continuity correction, less than or equal to 310 plus 0.5 to get up to the other edge of that histogram. And so then this normal interval that's going to be used to approximate the binomial random variable is going to be 269.5 less than or equal to x less than or equal to 310.5. Alright, so now let's look at another example. So let's find the probability of getting at least 158 successes. So remember, at least means greater than or equal to. So in this case, this is going to be the probability that R for our binomial random variable is greater than or equal to 158. So we still want to check for equality just like we did before back in chapter 5 with binomial random variables. So in this case, we have equality, so we're good. So let's draw our number line. So everything greater than or equal to 158 is everything from 158 on up to the right. So in this case, if we want to extend this to make it continuous because it's a left-hand endpoint, then we have to subtract 0.5. So this is going to be the probability that x now, as we do our continuity correction, is greater than or equal to 157.5 because we subtract 0.5 from 158. Let's look at one more example. So the probability of getting less than 63 successes. So strictly less than. So this is the probability that R is less than 63. So first thing to check, do we have equality? So we still have to get equality just like we did back in chapter 5. So in this case, we have just strictly less than 63. So remember, we want to rewrite this so that it's less than or equal to something. So less than 63, remember, if it's less than a value, you go down 1. So 63 is going to go down to 62. If it was greater than or just strictly greater than something, you would add something to it. You would add 1 to it to get up to the next number. But in this case, it's less than, so this becomes R is less than or equal to 62. Sketch our number line. So there's 62. Everything less than or equal to it is on the left-hand side. And so if we want to make it continuous, we have to add 0.5 because it's a right-hand endpoint. So this becomes the probability that x now, as we do our continuity correction, we're changing our variable, we're doing our continuity correction. So this becomes R is less than or equal to 62.5.